Graph Theory Class 4 Video 2. In this video we're going to talk about Eulerian graphs, in particular directed Eulerian graphs. So in the previous video we spoke about undirected Eulerian graphs, and we mentioned this very nice theorem which completely classifies when a graph has an Eulerian circuit or an Eulerian trail. As you can imagine, things are a lot more complicated when talking about directed graphs. Even a really simple looking graph like this, if it's undirected, it's very easy to understand, but by making it directed, it adds a whole new layer of complexity. Like if I make it directed in this manner here, then it's clear that this graph here does not have an Eulerian circuit. It's not Eulerian. Okay? You can't hit all of the edges. Whereas if I just change the direction of one of the edges, so if I make it like this, then this graph here is Eulerian. Okay? So the arrows add a whole new layer of complexity. And we're going to look at a theorem which is analogous to the theorem we looked at for the undirected case. So here's the theorem. It's important, but not quite as important as for the undirected case. So a directed graph is Eulerian if and only if two conditions, like the previous time. The first condition is it takes care of a technicality. So all the edges belong to the same strongly connected component. This is the same idea as in the previous one, where you're trying to eliminate cases like this. Okay, like if I consider this whole thing to be a single graph, then the edges, they don't all belong to the same connected component, so it's impossible for it to be Eulerian. Okay. The second condition is simply every vertex has deg plus equal to deg minus, and if you remember, deg plus means the in degree, and deg minus means the out degree. So in words, what is this condition saying? It's saying that every vertex has the same number of arrows going into it as it does going out of it. Okay? And I like this theorem. If you think about this theorem, it's sort of one of these situations where this is the minimal possible condition that you could ask for to have an Eulerian graph. You need it to be connected, and you need the same number of arrows going in as going out. And this theorem tells you that actually that's sufficient. So the necessary condition is sufficient in this case. Let's do an example of this theorem. So is this following graph Eulerian? And you do this by working out the in and out degrees of all the vertices. So this one here has deg plus equal to 1, and deg minus also equal to 1. This one here has deg plus equal to, I see 1, 2 going in, and deg minus, I see 1, 2 going out, equal to 2. This one over here has deg plus equal to 1, and deg minus equal to 1. This one here has deg plus, I see 1, 2, so that's equal to 2, and deg minus, I see 1, 2, that's also equal to 2. This one here has deg plus equal to 2, and deg minus equal to 2, and this top one up here has deg plus equal to 1, and deg minus equal to 1. So in each case, it's clear that they have the same in degree as out degree. Okay, like 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1. These pairs of numbers are the same in each case. So by the above theorem, there exists an Eulerian circuit. Okay, thus, and that that is what it means to be an Eulerian graph. So the graph is Eulerian. Okay, that's the end of this example, and it's the end of this video.